So overview of this project, I'm going to go through an introduction, the objective. I'm going to go through the model, how I set it up, the geometry, the mesh, the boundary conditions, the governing equations, all the different materials that I used in this simulation, and how and what software and hardware I used to model this. Then I'm going to go into the discussions, the results of the simulation, and I can give a conclusion afterwards and cite some references. So to begin, I am testing the structural integrity of different materials by using a ballistic model of projectile and flat plate. It's a little coupon model, simplified model to help understand how these materials behave under heavy loads in a short amount of time. There are many projectile and flat plate ballistic impact tests on coupon materials all over the internet and all over that have been tested. Most of the studies, however, they involve comparing very similar types of materials with a variety of test conditions, so they vary either speed or loads. But in this project, I'm going to be modeling very different materials. So I'll be modeling a ductile material, a brittle material, and a composite material. And specifically for the composite material, I'm going to vary the direction of the fibers and model it 3 times, each with the fibers going in a different direction. So the objective of this project is to understand how the projectile loads upon this material, these slew of materials. I seek to understand the difference between ductile, brittle, and composite material under a high impact concentrated load from a fast moving projectile. So to start on the model, the solid geometry that I created was created in the software, the CAD software NX version 9.0. For the projectile, I roughly try to model it at the same dimensions as a 50 caliber bullet. So you can see here's a quarter of the bullet, which I've created in NX. All these dimensions right here are in millimeters. And here is the flat plate. So again, this is a quarter model. The flat plate is roughly 6 inches by 6 inches and with a thickness of 1/2 inch. So after I created this solid geometry, I meshed it in ANSYS and it was reflected and copied to create a full model. I started the projectile about 1 inch away from the center of the plate. And so moving on, the geometry was meshed in ANSYS 16.0 Classic. For this mesh, the element type is 8-node brick elements. This is used for impact simulations because of the number of degrees of freedom. And for the flat plate, as you can see here, I gave the mesh a bias, so the mesh is finer in the center of the plate where the impact area is, so it's allows to be to have more freedom in movement, whereas near the ends of the plate it's a little stiffer. Here you can see when I brought the model into LS Prepost. In ANSYS, I used a script to orient all the elements. Every single element within the model has its own coordinate system, but if you can select the elements by layers, you can orient them, so you can orient them all in the same direction. So now that they all have the same coordinate system, and because they have the same coordinate system now, it allows you to apply a orthotropic material like a composite, where you can define the yield strength in all different directions now. Now going to the boundary conditions. So you see here is when I reflected and copied the quarter mesh around to create a full model. As you can see here that there's a finer mesh in the center and stiffer near the end. So the boundary conditions, I fixed the ends in all directions and in all rotations so it cannot move. And the projectile, I used just one test condition where I gave it an initial velocity of 500 meters per second. Here you can see is the LS Dyna keyword card, and in the model I had it as millimeters. Okay, now for the for the details of the material. So for the projectile, I kept the same material throughout the entire project. I gave it the materials of structural steel. Here you can see the density, elastic modulus, the Poisson's ratio, and the yield strength. This is a typical LS Dyna keyword card. And for this ductile material, I used the keyword matte plastic kinematic for a Dyna. For the flat plate, I give it a variety of different materials. For the first material, I used ductile material, I used aluminum alloy 1100 H14. And here you can see the density again, elastic modulus, Poisson ratio, and yield strength. So the yield strength here is this is megapascals, so 95 megapascals. And then for the density, it's tons per millimeter cubed, actually. For the second material, I used cast iron for the brittle material. You can see here the Poisson's ratio is a little lower, but the yield strength is more than twice as big at 240 megapascals. Here for the composite material, I used Kevlar 129 fabric epoxy that I got from a NASA paper. In the reference, you can see the link. But for this material, you use a honeycomb. Matte honeycomb is the keyword, the Dyna keyword that you use. Has a low yield strength of only 15 kilopascals and a low density. And right here, these are the load curves for the different directions of the fibers. And here you can interchange the numbers of load curves to change the fiber directions. For the solver, I used the LS Dyna version 9.7. For the pre and post processing of the model, I used LS Prepost, and the model was run on 4 CPUs with 100 megabytes of memory. Okay. Here I compared the ductile and the brittle material. Here with these materials, the best way to compare them is the plastic strain. I gave roughly a plastic strain failure of 15.15. So here's aluminum flat plate and the cast iron flat plate, and you can see the difference as you scroll through this simulation. As I go through it, you can see how the aluminum plate that allows for large deformation, but the loading is very localized. Here, because for the cast iron plate, since the yield strength is pretty high, the projectile does not penetrate penetrate fully. It's only partial penetration, and because of that, it has a more global living throughout the. Now, as I go into the composite material, now I have you can't really compare the plastic strains. So here I'm comparing the von Mises stress, and here you have fibers oriented in the z direction, x direction, and the y direction. So here we can compare the differences between how the fibers are oriented. And here I use the what the yield strength as the highest level of the contour plot. So as you go through it, you see it's somewhat similar for all of them. However, the way the stress is distributed throughout the material is different. As you can see over here, the stress is all very localized in the impact area, but as in where the fibers are in the y direction, it is distributed a lot more, and there's a little bit